All righty. Okay, there we go. So we covered activators and deactivators, and we saw the activating groups like a methyl or a methoxy were ortho and para directors, and that an electron withdrawing group or a deactivator, like a nitro, was a meta director. Well, now we're going to talk about the exceptions, which are the halogens. And so it turns out that the electron that the halogens, they actually withdraw electron density, don't they? Because they're deactivating on account of electronegativity, right? If you think fluorine, chlorine, these are very electronegative atoms. However, they can actually donate electrons through resonance. So they're electron withdrawing via induction, but they're electron donating through resonance. So, it's kind of like you got two things going on here. And so here is a picture of chlorobenzene, and then we see, yes, it's got a dipole going towards the chlorine. And so the chlorine is deactivating, right, because of induction. But again, if we look at the resonance structures drawn down here at the bottom, you can see that the chlorine can also donate electrons. All right. So which one is it going to be? What's going to happen here? All right. And it just turns out that when you draw the resultant sigma complexes that you get after ortho and para attack on an aromatic ring with a halogen on it, that when you look at the sigma complexes from the ortho and para attack, again, you end up with one extra resonance structure in each case. And so that is why the halogens, even though they are electron withdrawing and they're deactivating, that the substitution reactions are going to occur preferentially at either the ortho or the para position and not the meta position. Why? Because we get an extra resonance contributor in both cases. So there you have it. Again, even though they're deactivating, they're still going to cause substitution to occur at the ortho or para position. All right. So I'll have my students, like I said earlier, ask me sometimes, Mr. Dion, do you have this all summarized in a table? And I think that all of this information is summarized in table 18.1. So if you're wondering where I'm getting the information on these slides that I'm going to go over for the next couple of seconds here, this comes from table 18.1. So we could even scribble that on here, table 18.1. And when I teach the class in person, normally what I'll do is I'll actually print out a copy of table 18.1, like literally a hard copy, and I'll hand it out to the class. So table 18.1, extremely important. And you're probably going to need to print it out when you're studying, okay, just to get the ball rolling until you memorize the strong, the moderate, the weak activators, and then the weak, the moderate, the strong deactivators. All right, so let's get into it. What's going to be a strong activator? Remember that activators are ortho-pair directors. So if you have any kind of group that's got a lone pair directly attached to the ring, and there's no way that it can be involved in resonance outside of the ring, then it's going to be a strong activator. All right, so it could be a phenol, it could be a phenoxide, it could be an aniline, a primary aniline, a secondary aniline derivative. Those are all considered to be strong activators. And then you're probably sitting there looking ahead of me and going, well, Mr. Dion, based on that rationale, why isn't an alkoxy group considered to be a strong activator? An alkoxy group is actually somewhere in no man's land. It's kind of like in between strong and moderate. I even have in my notes, I literally wrote the words kinda in between moderate and strong. So you can even write that in here, moderate slash strong, the alkoxy group. So if you have a lone pair of electrons on an atom right outside the ring, but it can participate in resonance outside of the ring, like these can, and these can, obviously, and these cans here. So if you have a situation like that, right, you're going to end up with a moderate activator, right? So the electrons are, you can delocalize them inside the ring, but outside of the ring as well. So that would be considered a moderate activator. The next one, weak activators, right, are going to be any kind of alkyl group. Any kind of alkyl group could be methyl, ethyl, propyl, butyl, tert-butyl, etc. Right, and remember that these are electron donating. So alkyl groups are, we'll put here, alkyl groups are electron donating via hyperconjugation. Hyperconjugation. All right. And if you don't remember hyperconjugation, it's covered in section 6.11 of our textbook. So way back in Organic 1 is when we covered that. All right. So now we've covered all the activators. Well, let's get into those deactivators. And we saw a really strong deactivator before, right? A nitro group. That is a really powerful deactivator. It pulls electron density away from a ring like crazy. Also, if you have some kind of aniline derivative, so you have 3 alkyl groups on your nitrogen, which gives it a positive charge, well, of course, that's going to pull electron density to try to stabilize that positive charge. And so that would be deactivating. Also, if you have some kind of trihalo alkyl group, so if you have, right, like CBr3, for example, and you probably saw that molecule towards the end of the slide deck, that would be a really powerful deactivating group. Since you've got so many halogens, it pulls electron density away like crazy. Moderate deactivators, you can see they have something in common for the most part. Anything that's got a carbonyl directly attached to the ring. Okay, if you've got a carbonyl attached directly to the ring, man, you have got some kind of moderate deactivator. If you have a sulfonic acid, that's also a moderate deactivator, and a nitrile. So a nitrile would also be a moderate deactivator. All right. And then when it comes to the weak deactivators, well, we said that the only weak deactivator that we looked at was the halogens. But remember, they're an exception. Okay. They're deactivators, but they're ortho-para directors. All right. And that's all of the information you need to know. And this, again, is all summarized in table 18.1. Here's that table right here. Okay. And again, I recommend, I would say print and memorize. Okay. And of course, you're just going to print it out because you're going to need to use it in synthesis problems. And if I can tell you, a better way to budget your time rather than just sitting down by a campfire with this table and being like, let me memorize this. No, I would not do that. I would start working on practice problems immediately and then try to apply the rationale in here rather than just try to memorize a table. That won't get you too far in organic chemistry. You need to know how to apply the table, right? Okay, so let's get into some of that. Let's try applying the table here. And yeah, I'll ask you guys some questions. So I realized that for the last, 45 minutes or so, I didn't ask you many questions because there's just so much content to get through. So let me ask you a few questions here. It says for each of these compounds, predict whether the ring is activated or deactivated, then predict the strength. Is it moderate, weak, strong? And then finally predict, the expected directing effects. Boy, all kinds of stuff here. So we'll start with the first one, which is nitrobenzene, A. So I'll ask you guys first, is this going to be an activator or deactivator? A nitro group. Heck yeah. Oh, thanks, Chaylin. You answered 2 things for me. So thanks. So Chaylin said, not only is it an activator, it's a strong, sorry, did I say activator? A strong deactivator. There we go. Strong deactivator. And where's it going to direct to? Will it be ortho, para, meta? Heck yeah. Meta. Perfect. Man, you guys are so fast. All right, the next one, we've got a carbonyl attached directly to the aromatic ring. Notice that I never used the word functional group. I never said amide, amine, because an amide or an amine, like you got to be very careful with that kind of parlance when you're studying this. But we have a carbonyl here. So is this going to be a moderate or a strong deactivator? It's a deactivator, right? Because it's pulling electron density. Yes, it's moderate. So we'll put here, where's my pen? Moderate deactivator. And if it's a deactivator, it's going to direct it to the meta position again. Good, excellent. So the first one was the nitro, right? The next one, we've got a bromine. That's the halogen. That's an exception. We know that it's a weak deactivator. The weak deactivator. And it's going to direct to the ortho and para. So we'll put ortho para director like this. And then the last one's a little bit tricky, isn't it? Because that wasn't in the table that we looked at. But if we think about it, look, you've got, right, you've got this carbon with a double bond to nitrogen here, okay? And so you do have a dipole going this way. So it's kind of like as if you had a carbonyl in a way, right? So it's going to be pulling electron density away. So this would be considered a moderate deactivator as well. Okay, and if it's a moderate deactivator, it's going to be a meta director too. So this is where you have to be really kind of on your toes as a student in organic chemistry. So let's copy this and we'll paste it down here. So moderate deactivator, it's going to be a meta director. Give me a thumbs up if you're with me on that. Any questions about those four? The last one, you kind of have to apply your knowledge a little bit, right? Okay, good, good. All right, let's move on from there. And I thought I had another question here. Oh, maybe I didn't. All right. Well, let's turn our attention to, now that we've studied, table 18.1, and we kind of have that down. So at this point, you're assume table 18.1, or right now you're probably just going to hold it next to you and study it while we work on this. So it says the directing effects of all the substituents attached to a ring must be taken into account in an EAS, or an electrophilic aromatic substitution reaction. The directing effects of the methyl and the nitro direct the bromine to the same carbon. So you only get one product, right? This is a great problem to have, this one here. Right, you see you've got a methyl group. Well, that's an orthopara director. And then you've got a nitro. That's a meta director. Well, the nitro is directing here, and the methyl is directing here. So they're both directing to the exact same place. So your bromination is going to occur ortho to the methyl, and of course it's going to be meta to the nitro. So that one is everything set up for you, okay? So you're probably wondering, well, what if I have two groups that are directing to two different carbons? That's really where we're going with this, right? What do we do then? Okay, so let's take a look at the rules here. It says, if the groups direct to different carbons, here's the rule. The stronger group is going to dominate. Okay, so the stronger activating group is what it should say. Okay, there you go. So let's take a look here. Let's say you have, what's this example here? We've got this paramethylphenol is what you would call this. It's got another common name that escapes me at the moment. But you see that we have a strong director up here to the ortho and para positions. Well, there's the ortho positions. The para position is blocked, so it can't go there. And then you've got a weak ortho para director. There we go, weak. That's going to direct here. And then, of course, your para position is blocked. So, where's it going to go to? It's going to go where my yellow highlighter is, right? Because the hydroxyl, the OH group, is a stronger director. So your nitro goes there. Give me a thumbs up if you follow me on the rationale there. Just the stronger one wins. Yep, the stronger activator wins. Is what it should say, really. Okay. So, one of my students, and I repeat myself like an old man all the time now. At least I'm aware of it. Once I become unaware of it, that's when it's going to be really bad. But one of my students said a number of years ago, he said, organic chemistry is learning a bunch of rules and then all the exceptions to those rules. But these aren't exceptions, but these are the guidelines that we're going to use when you've got, some different possibilities here. So let's take a look at some guidelines for deciding what's going to happen when we have multiple substituents. Okay, first thing is this. If you have a mono-substituted ring, the para product is usually going to dominate, right? Why? Because of steric hindrance, right? You know that you have free rotation about this bond, and so these positions are going to be more sterically hindered, and so your nitration would occur in the para position. I'm going to write down here, though, remember, toluene is an exception. An exception is that we get more at the ortho position, we saw, but that actually depends on the reaction conditions, okay? So it depends on conditions. And if you're wondering, are we going to look at those conditions? The answer is no, just more of an FYI thing. I'll just throw it out there. Number two, if you've got two groups that are 1,4 to each other, so you get two groups that are 1,4 to each other, the substitution is going to occur at the less sterically hindered site, right? So this isopropyl group is directing to these two ortho positions, And then the methyl group is directing to these two ortho positions, right? The both para positions are blocked. Well, since the positions in green are more sterically hindered, it's going to go to the position in yellow, and that's where we're going to get our major product. So that's another one. And here's another rule. If you have 1,3 dye substitution, you almost never get anything right in between. Okay, that very, very rarely happens. So then you would do it based off of sterics, all right? So if we look at the isopropyl group, okay, that's directing to the ortho and para positions. And then if we look at the methyl group, that's directing to the ortho and to the para positions. So which position is it going to go to? It's not going to get, well, let me get my red pen. It's not going to go here because that's in between two groups. So that's too sterically hindered. And this one is more sterically hindered than this one. And so the one I have in the red circle, that's where it's preferentially going to occur. It's like a little puzzle, right? But you have to have a solid working knowledge of table 18.1 in order to be able to apply this. So you might be wondering, well, what if I have, what if I have something like this where I do have an R group like that's bigger than a methyl group, and what if I want to put a substituent, in the ortho position, right? What if I want to put something there? How would I do that? Is there a way to do that? And the answer is, yeah, there is. Okay. And what we do is we use something called a blocking group, not a protecting group. If you remember back in the alcohols and phenols chapter, a protecting group was something that we used to mask a functional group, right, to kind of cover it up. But now a blocking group actually blocks a position. Okay, it prevents a reaction from occurring at a certain position. So let's say you wanted to take this molecule, tert-butylbenzene, and you wanted to convert it into 2-bromo-tert-butylbenzene. If you just treated this molecule with bromine, so Br2 and FeBr3, I mean, you're only going to get bromination occurring in the para position, right? A tert-butyl group is just humongous. I mean, so big, you're only going to get this. So how would you install the bromine at the ortho position? Well, the way you would do that is you would block the para position. So you would put some kind of blocking group in the way, then you do the bromination, then you remove the blocking group, and there you go. So if you're wondering, like, what's the blocking group? Well, do you remember the old chestnut, the sulfonic acid that we looked at with the fuming sulfuric acid? And then we said it could be removed with dilute sulfuric acid. That's going to be our blocking group. It's going to be a sulfonic acid. So that's the utility of the sulfonic acid, right? Again, the reason why the sulfonic acid is used is because sulfonation is reversible. You can do it in one way, and then you can do it this way, and then you can rip it off. And all you need are cheap reagents, concentrated fuming sulfuric acid to install it, and just a little bit of dilute H2SO4 to remove it. Not too bad, all right? So let's take a look at the synthesis shown down here. First thing you would do is install blocking group. So install blocking group, your sulfonic acid. Now, the sulfonic acid, if you don't remember, the sulfonic acid is a meta director, right? And the tert-butyl group is going to be an ortho director. So it's only going to direct to that position, right, that I have with the yellow and the green highlighter. So you do the bromination, and then you remove blocking group. So remove blocking group, and that's it, man. That's it. Isn't that a pretty cool synthesis, or what? Organic chemists are pretty cagey, right? They always have some kind of sneaky way to sneak up on some kind of molecule that they want. All right, so with all that in mind, let's turn our attention to another practice problem here. It says for each of the compounds shown, identify which positions are most likely to undergo an EAS, remember, electrophilic aromatic substitution reaction. So let's take a look here. Wow, we're going to have to really investigate this guy. Okay, so we've got the methyl group. That is an ortho and para director. We see that the two ortho positions are blocked, so we can just scratch that out. And then we see that the nitro groups, oops, where's my yellow highlighter? Where do the nitro groups direct to? To ortho, para, or to meta? Who remembers? Yeah, meta, exactly. So there we go. So you can see that both of these groups directed the exact same place. So that one was pretty quick, okay? Everything directs to this position. So I'm just going to delete the highlighter. Okay, Let's take a look at the next one. Okay, same rationale. We have a methyl group. It directs to the ortho and para positions. These two are blocked, so we'll scratch those off. Then we have this nitro. It directs to meta, but this meta is blocked. Then we have this nitro. Let me highlight it in red. Okay, this nitro is directing to this meta position and this meta position, but the first one is blocked. And so we only have, where's my yellow highlighter? We only have one spot where the alkylation or acylation or whatever, the EAS reaction can occur. And so it's going to be this carbon right here. Everybody follow me on that? Give me a thumbs up if you're with me on the rationale. For that one. Okay, so let's take a look at the next one. Okay, let's draw the lone pairs in here. So, let's see. There we go. So we've only got 3 carbons open. We've got this carbon, and this carbon. Is anybody able to figure out where the substitution is preferentially going to occur for this one? Would it be blue, red, or yellow? All right, let's take a look at it. Let's take a peek at it. So let's see here. First of all, let me erase it, all these. Okay, and I'll kind of start over here. Let's start with this group. Okay, we've got this ester over here. So what is this going to be, an activator or deactivator? This group? No, this is going to be a strong activator, right? So an ester can be one of 2 ways. Okay, so if you have an aromatic ring and you have an ester attached by the carbonyl, like that, that's going to be a moderate deactivator. But if you have the ester group attached like this, right, if you switch it around, now this is going to be a moderate activator. All right, does that make sense? Right, you flip them around. Exactly. So this is going to be a moderate activator. Okay, let's try all of these. This one here, so what's this one going to be? This one's going to be a moderate deactivator. And then what about the methyl group? Well, that's going to be a weak activator. So weak activator. So now that we have all that figured out, we can see that the ester that's circled in red, that's going to be our strongest activator here. It's because it's moderate. Everything else is weak or a deactivator. That's going to direct to the ortho and para positions. Well, we see that 2 of the positions are blocked. Only one of them is open. Right? Only one of them is open. So that's probably where everything's going to go. And the one that's the weak activator, is going to direct to the ortho positions and to the para positions, but it's weak. So we don't even have to worry about those. We still always go with the strongest one. And then if you look at the moderate deactivator, that's going to direct to the meta positions. And so it's directing the same place as the moderate activator is. And so the substitution reaction is going to occur at this carbon here. Everybody with me on that now? Cha? All right. Yeah, you have to think about it a little bit, right? Okay, well, let's look at the last one here. We've got the methyl groups, right? Those are going to direct to the ortho positions and the para position, which would be up here, but the para position, oops, sorry, my mistake. They are going to direct, okay, let's do the first one. The first one is going to direct to the ortho and para positions. The second one is going to direct to the ortho and para positions, right? But you can see that this position is blocked, so we'll leave that here. And then the nitrile is going to be a deactivator because it's electron withdrawing, right? This is a deactivator. It's a moderate deactivator. And so it's going to direct you to the meta position. Oops, where's my green highlighter? So that would be these positions. So the only place it's going to go are those 2 positions. So I'll just put a circle around it. There we go. So it's going to go to one of those positions right there. All right. Will you have to practice that a little bit? Yes, absolutely you will. Okay. It's normal. If you didn't, you'd be like Goodwill Hunting or something. Okay. Everybody has to practice this. Let's try a couple more practice problems here. Let's turn up the heat. see if we can figure this one out here. Okay, let's do this one a little bit differently, okay? This one says for each of the following compounds, determine the position that is most likely to be the site of an EAS reaction. So E, electrophilic aromatic substitution. Let's do this. If I highlight the phenol or the hydroxy in green, the nitro in yellow, and the methyl in blue, which one of these is the strongest activator? Right, the green one, right? Absolutely. So we could just go based off of that, right? The strong activator is going to direct to the ortho and para positions, but we said we never get anything showing up in between positions 1 and 3, and we don't get anything in the para position because it's blocked. And so it must be occurring here, okay? And if you look at the other groups, neither of them are directing to that position, but again, this one is the strong activator. So it's the winner. There we go. Winner, hydroxyl group. Okay, let's take a look at the next one. I'll highlight the methoxy in yellow, the nitro in red, and the bromine in blue. So which one is going to be the strongest activator here? Going to be the strongest activator, right? Nitro is a deactivator. So the strongest one is going to be the methoxy group, right? A nitro is strongly deactivating, right? We're looking for the strongest activator, right? And a nitro, or I'm sorry, a methoxy is kind of like strong / moderate activator, activator. And so it's going to activate the ortho and para position. So ortho and para, the para position is blocked. This position, we don't get anything at 1 and 3. And so where the alkylation or acylation or nitration or whatever is going to occur would be at this carbon right here. All right, we got one more. Let's give it the old college try here. You've got 2 deactivators, right? These are 2 moderate deactivators. We'll put here both are moderate deactivated activators. All right. So that means that this group, this aldehyde, is going to direct to the meta position. And this guy is also going to direct to the meta position. So which position do you think substitution would occur at? Maybe I'll do it at the green, on the green position or the blue position? Since they both have the same strength. At the green, right? Because of sterics. Exactly. We'll go, so we'll do this, Tiana. We'll circle it and we'll say here because of sterics. Boom, done, just like that. All righty, cooking with gas now. All right, let's see here. Determine whether you would need a blocking group. All right, remember the blocking group, the blocking group, okay, remember it's a sulfonic acid, right, that you install with fuming concentrated sulfuric acid. So for the first one, if you try to do a nitration on cumene, on this molecule, if I highlight this position in green, this position in blue, and this position in red, where would the nitro go if I just treated this molecule with nitric acid and sulfuric acid? Where would it go? Would it go with the green carbon? No, it's going to go in the para position, right, based on sterics. And so we need a blocking group. So for let's, instead of writing need a blocking group, let's just write out the synthesis, okay? So first, we would take our starting material, okay? So isopropyl benzene, which I told you is called cumene, and we would install our blocking group. So fuming H2SO4, and that's going to install the blocking group in the para position. All right, SO3H. Right, like that. All right, and so next we're going to install our nitro group. So you have to know the conditions for nitration. So it's going to be nitric acid and sulfuric acid mixed together. And that's going to affect the nitration. And of course, now it's going to go ortho to the stronger activator. right? This is a deactivator. This is a weak activator. So it's going to go where the activator directs it. So it's going to go in the ortho position to the isopropyl group. So we get our nitro group in here. There's our sulfonic acid. And then to get to the product, I'll just kind of shorten it here. We do use dilute H2SO4, and you are done. Just like that. All right. Let me just draw a little line here to separate these two. You got to keep them separated, right? Anyhow, what about B? Would we need a blocking group in B? I'm sure somebody's looked ahead. You need a blocking group in B? No, right? Remember, the isopropyl group is a weak activator, and it's going to direct preferentially to the para position. So all you need for that one is just some, we'll put here bromine, Br2, and FeBr3 as our Lewis acid catalyst. And there you go. We're done, just like that. So let's move on to section 18.12. Before we take our next break, and I tell you to try some synthesis reactions, on your own, let's take a look at some of the synthesis strategies, okay? So we've learned 10 different groups that can be installed on the benzene ring. A couple reactions in here I just want to remind you of. So one is benzylic bromination. Okay, so if you use NBS, you can exchange a benzoic proton for a bromine. And so if you use excess NBS, that's going to exchange all of the bromines, all of the hydrogens for a bromine. So you go from a weak activator to a strong deactivator. And I'm going to cover that again in a few seconds. Another one that I haven't really talked about, but we did talk about previously, is converting oxidizing a benzylic position using chromic acid or using potassium permanganate followed by aqueous acid. So that's a good way to do a benzylic oxidation to make a benzoic acid derivative. And that really covers everything. Okay, that's everything. We've covered everything on here. And what's really cool about all these reactions, that once you know them frontwards and backwards, you can start to synthesize molecules like this. So my question to you is like, if you wanted to install a bromine and a nitro on benzene, right? If you're starting with benzene, I mean, which one of these are you going to put on first? Would it be the bromine or the nitro? Well, the bromine is going to be an ortho para director, and the nitro is a meta director, and the two groups are meta to each other. So that means you have to put this group on first and this group on second. Give me a thumbs up if that makes some sense to you. And stop me if it doesn't, because if it doesn't, I'll go back over it again. Okay, so as long as you understand that, you're going to see that most of the problems in this chapter are really just kind of puzzles, okay? Somebody wrote in the chat, and I'm actually going to read this in front of the class, and it's going to go on YouTube. Somebody just put in the chat, this chapter is wild. Okay, it is, right? There's so much content and little kind of nuances here, right? Aren't there? And believe me, didn't I warn you ahead of time? I told you that there was, right? I made sure to say that to you many times, okay? So let's take a look here. This is a really neat table. I took this class in 1995, and they didn't show me this, okay? I had a version of table 18.1 in my textbook. The woman who wrote my textbook, she died a long time ago. She was from University of Michigan. But anyhow, she never had this table in here, but I really like this because it shows students how you can take, a meta director, convert it into orthopara, or the opposite. So it gives you some really neat transformations. Like, check this out. For example, if you install the nitro group, right, just using nitric acid and sulfuric acid, well, nitro is meta directing, right? But if you reduce it to an aniline, then you make an orthopara director, right? So you change the direction just by doing one reaction. Another good example would be, let's say you take toluene. Well, toluene is an orthopara director. If you do a benzoic oxidation, you convert it to a benzoic acid derivative. Okay, and here they just made benzoic acid. So you use potassium permanganate, water, and you cook that up, and that makes the benzoate salt. And then you protonate that in the second step with aqueous acid. Well, again, you go from an orthopara to a meta director, or I guess that's not what I said before. But anyhow, and then what's the other two that they show you? I mentioned this one on the little wheel of reactions there. Wheel of reactions, right? So where you take the methyl group, which is orthopara directing, you convert every proton or you substitute every proton for a bromine, and then you make a meta-director. And then the last one here is the Clemmensen reaction, right? Clemmensen reduction. You take a meta-director and you convert it into an ortho-para-director. I don't know. I've never told a student in my life, memorize this table. It's not really about memorizing this table because you have to memorize all these reactions anyway. It's more about look what you can do, okay? Look at the neat things you can do with all these different reactions that you've learned, all right? And you're like, yeah, cool, yeah, sure. Anyhow, okay, so let's take a look at a synthesis problem. This is a really good, I shouldn't say good problem to have, but it's an interesting problem, right? Let's say somebody said, I'm going to pay you loads and loads of money if you can make this molecule, right? If this chapter gives you appreciation for anything, it should be how many reactions a good organic chemist would have to know in order to design, new molecules, to be a medicinal chemist in the pharmaceutical industry. Anyhow, if you look at these two groups, the amino group is ortho-para-directing, and then you got a chlorine that's also it's also ortho-para-directing. So what the hell do you do in this kind of case, right? You've got to be able to think backwards and say, well, the amino group that could come from a nitro group. In a nitro group, I could install that first, and that's a meta-director, right? So that's why you kind of have to know all those reactions on table 18.2. Give me a thumbs up if you're with me on at least the rationale. Just yes, that makes some kind of, and when I say that, it's not just to make me feel better. If you want to stop me and say, I'm not so sure. Yeah. So there we go. So, you've got to install that nitro first, then you can put the chlorine in the meta position, right? And this is, again, the same kind of rationale comes up all the time. You've got to be able to think backwards, right? Retrosynthetically to determine which group you should install first. So what would you do? You do the nitration, right, in the first step, followed by chlorination, and then you would do the reduction. So zinc and HCl, and you could heat that up, and then sodium hydroxide, and there you go. So check this out. It says in most cases, changing the order of the reactions is going to change the substitution pattern. So I would say here, be careful. Okay, be very careful when you're choosing your reagents. Now, when I say be careful, that does not mean be afraid to make a mistake when you're practicing. Do not be afraid to make a mistake. Okay, you've got to make room for mistakes in organic chemistry. You have to make them in order to master all the content. So, are you ready? Now I'm going to show you the limitations for synthesis, and these kind of have to be memorized. Okay, so again, I showed you some limitations of Friedel-Crafts before. Now I'm going to show you the limitations of synthesis. So I'll put here memorize. All right, and they are somewhat rational. Okay, somewhat rational. First one, you can't nitrate an aniline derivative. So if you have an amino group on your ring, you cannot do a nitration. Why doesn't it work? It's because you end up oxidizing the amino group and you basically destroy it. Okay, so that doesn't work. If you've got an amino group, you can't install nitro, it just doesn't work. Okay, first thing you do is protonate the amino group because it's a base, and then it just goes from hell, goes to hell from there. The next thing is Friedel-Crafts do not work when you have a ring that's moderately or strongly deactivated. Okay, if you have any kind of moderate or strong deactivator, Friedel-Crafts, and that means Friedel-Crafts alkylation, or acylation. Acylation. Neither of them are going to work. They just don't work. Okay. So those are the only two limitations. But in my notes, I've got my notes in front of my face. I noticed I put a big star on both of these pages. Okay. What I have on, I got a big green star on the first one, and then I have a big green star in the second one. So I'll put it. It doesn't mean you have to memorize the mechanism. It just means don't forget these rules. Okay. And they can escape anybody's memory. So make sure you commit those to memory. So with all that in mind, let's try some synthesis here. 18.26, it says starting with benzene and using any other necessary reagents of your choice, design a synthesis for each of the following compounds. Note, some of the problems might have more than one plausible answer. That's something you're going to see more and more of as we move along, right? More than one plausible answer. Not that every question has a million answers, but some of them have more than others. All right. So let's see here. What I think we should do is take another short break, and everybody should give these a try, and then we can come back and finish them. But before we do that, why don't we try the first one? We'll try the first one together. We're going to start with A, and we want to take benzene, and we want to make that compound, right? We want to put an amino group and a bromine ortho to each other. So if we want to have two groups that are ortho to each other, which one of these groups are we going to install first, do you think? Would we put the bromine in first or the amino group in first? I'd say we're going to put the bromine in first, right? Because the only way that we could put the amine in first is by a nitration. And then a nitro group is an meta director. So that's not going to work. And then if we reduce, if we reduce the nitro to the amine, that's an ortho pair director. But then if we treat that with an acid, we're gonna, we could do a protonation there. So that wouldn't be good. So I don't think that's the best strategy here. I'd have to look to see what the solutions manual says about it, but I would go with the bromination first, okay? So let's see, what would happen if we installed the bromine first? So if we do bromine and iron 3 bromide, let's just throw a bromine on it. All right, so there we go, like this. And now we want to put an amino group here. So we want it to be ortho. So we know that bromine is an ortho para director, but we want to direct to the ortho position. So what are we going to have to do to prevent from the nitration occurring at the para position? What kind of group do we have to use? Starts with B, ends with blocking. That's right, a blocking group, exactly. So we're going to use a blocking group. So fuming H2SO4, and that's going to install our blocking group, the sulfonic acid. And there we go, like that. So remember, this is an ortho para director, and this is a meta director. So everything is directing to this position. Excuse me. And so now we can do our nitration with our nitric acid and sulfuric acid. And so we put in that nitro group. So we've got our nitro, we've got our bromine, we've got our sulfonic acid, like that. And now we need to remove the blocking group. So let's do that. And for that, we use dilute H2SO4. Right? Like that. I'm kind of running out of space here, aren't I? And so the last step to get to the product is just going to be the reduction. So I'll use iron in HCl in the first step. And then for the second step, we'll use sodium hydroxide, NaOH, like that. And that will give you the product. So somebody says, why would you need a blocking group if the major product is going to be ortho versus para, even without it? Because remember, Tiana, everything, the major product is always going to be para, unless it's toluene. So with everything else, it's always, it's only toluene that gives you the ortho product is the major. Everything else, just assume it's para. Cool? Yeah, great question. Yeah, great question to pick up on that. All right, so why don't we take a short break, and then we'll come back and we'll try, why don't we try, we'll just try maybe B after the break, and then maybe we'll look at C on Monday morning, right? Because we're going to talk about this, or sorry, Monday afternoon, because we're going to take a look at this chapter again then. So why doesn't everybody try question B here? And then I'd also like you to try and solve 18.28a. So there's 3 groups on this one. So you're really upping the ante on this one. So again, I'd like everybody to try 18.26b and 18.28a. And then after we do those, I'm going to cover the last couple of sections, which deal with SNAR chemistry. So that's a few slides. And then we do elimination addition, which is the very last reaction that's learned in the whole chapter. And then after that, it's just a matter of, kind of reviewing the mechanisms that we covered. Okay, so again, we're going to do those two problems when we come back, and we'll look at the last two sections of new reactions, which aren't electrophilic aromatic substitution. They're SNAR and elimination addition, and then we'll be done the material, and that way we could focus on practice on Monday.